All right, it's time to start. Welcome back. So we do have the homework due tonight. I hope you've had a chance to check it out. Please let me know if you have questions about it. I'd be happy to try and help out by email. I do, every week for the full hour before class, I'm going to be sitting around. So if you do have homework questions, that's a great time to come and chat about it. Or although we can set up other times also. Some people have asked me about how exactly is the homework going to be graded. So here's how I'm going to do it. I will tell you again later on if you like. I'm going to choose 4 questions out of the assignment at random and grade them in detail, and you'll get points based on, did you do it right or not. And then you're also going to get some points just overall for sort of completion. So that's the idea. Yeah.
Do we get like partial if we did get the question?
Yeah, sure. So I'm going to look at each individual question will be worth 3 points. There are 4 of those, and then 3 more points for did you do the assignment, basically. So it's all out of 15, 3 points each. So you get partial credit, unless you do something completely inappropriate. All right, great. And we also have our first quiz will be on Friday. I hope you are looking forward to the first quiz. As I said before, the quiz is not meant to be super stressful, so we're going to take the first 10 minutes of class, do the quiz. You should expect it's typically going to be 2 questions, similar to the homework ones. Some of the homework ones I think are a little tricky. On the homework, I intend to give you some that are a little hard. On the quiz, I am going to try to make them sort of routine that you can do. The idea is if you did the homework and it made sense to you, then you should be able to do the quiz problems, no problem. So I would also like for you to submit the quizzes on Gradescope. So bring your phone. I hope you all know how to get to the Gradescope. And on Friday, we'll just start off at the very beginning, do the quiz, you'll all send it in, and then we'll go on with the rest of the class. That's how I want to do it. Any questions about that? All right, great. It's going to be great. Okay, let's continue where we were talking last time. We sort of started discussing an interesting example of a DFA, which does what is kind of a hard computation, or at least not non-obvious computation. This was about binary numbers. So this is a DFA to accept binary numbers that are divisible by 3. All right. This is a task which actually, I don't even know how to do that. If you showed me a big binary number, how can you tell if it's divisible by 3 or not? It's not easy. Although I suppose that may be just for cultural reasons. I'm unused to working with binary numbers. Maybe this wouldn't be so hard if I was really into binary. But anyway, a DFA which reads a binary number as a string from left to right and decides whether or not that number is divisible by 3. That's the idea. I'm going to close the door. As I said at the end of last time, the idea is, think about as you read your string, 1 digit at a time, as you read your binary string, each new digit you encounter is either a 0 or a 1. And how does that change the value of the string as you've seen it so far? And what we said at the end last time was, if the next... I'll say it like this. I'm going to try and say this like I said it last time. If we've seen so far the number x and we read a 0 next, that is on the right, because we're reading the string left to right. If so far the number we've read was x, and then the next digit, the next binary digit is a 0, then the effect of that is to change the number to 2 times x. This is multiplying the number by 2. Just like in base 10 numbers, when you add a 0 on the end, that multiplies the number by 10. Since we're doing binary, it multiplies by 2. So if we've seen x and we read a 0, then the new value is 2x. And if we read a 1, same business. If we read a 1, the new value is 2x plus 1, right? Adding a 0 on the end of a binary number multiplies it by 2. Adding 1 on the end, well, it's like you added a 0 on the end and then added 1. So it's 2x plus 1. All right? This much I said at the end last time, I think. But this is a clue about how our DFA is going to work. In each step, each arrow will be either reading a 0 or a 1. And the effect of each of those will be either to multiply the number by 2 or to add 1 to the number. Now, when it comes to, this was the first sort of insight that's necessary to make the DFA. I also mentioned last time that you only need 3 states to do this. When it comes to divisibility by 3, when you divide a number by 3, actually there's only 3 outcomes. Either it is divisible by 3, or it's not divisible and you have a remainder of 1, or it's not divisible and you have a remainder of 2. Those are the only things that can happen when you divide. So those are actually going to be our 3 states. I'm going to write 3 states here. And we're going to have to draw a bunch of arrows. But I'm going to call one of them is x equals 0 mod 3. That means x actually is divisible by 3. Another I'm going to call x equal 1 mod 3. And another x equal 2 mod 3, right? Those are the only possibilities. Can anyone say which one should be the accepting state? The 0. Someone's giving me the hand signal. The 0, yeah. That would be x equals 0 mods 3 means x is actually divisible by 3, and those are the ones we want to accept. So this I'm going to make an accepting state. And also, that should be the starting state, because when you start with the empty string, I'm going to interpret the empty string as the number 0. And the number 0 is 0 mod 3. To draw the arrows, and this is the interesting part, or the hard part, you have to decide for yourself if, for example, if my number is 0 mod 3, and then the next digit is a 0, this has the effect of multiplying the number by 2, and then where will it be after that? When you multiply a number by 2, if it was 0 mod 3, what's it going to be after you multiply by 2?
0.
Yeah, it's still going to be 0 mod 3. That's because, I mean, for this one I could reason it like, if it's divisible by 3, and then I multiply it by 2, well, it's still going to be divisible by 3, right? In fact, now it's divisible by 6, which is also divisible by 3. Anyway, there should be 0 like that, right? That was a bit of abstract reasoning that actually it's a little bit easier to, I'm going to write this in a more formalized way. Check it out. I'm going to explain in a more formal way what I just said, although I'm going to try to explain in a way which easily generalizes to the other cases. So I'm going to say if x equals 0 mod 3, then, check it out, we can say something like x equals 3 times k, right? For some k. X is a multiple of 3. So 2x equals 2 times 3k, right? Which is 3 times 2k, which again is 0 mod 3, because it's still a multiple of 3, all right? I did this little rewriting just because I wanted to see, yes, it really is just 3 times another something, all right? I hope everybody can see that. And so, if that means if I start in the 0 mod 3 step and I multiply it by 2, then I end up still in the 0 mod 3 step, all right? Whereas, what if I, instead of multiplying by 2, what if if we see a 1 next, it becomes instead 2x plus 1, which would be, 2 times 3k plus 1. I'm still considering the case when x equals 3k, right? If instead of going to 2x, I go to 2x plus 1, it's now 2 times 3k plus 1. Sorry, I'm down at the bottom there. And what is this when we consider mod 3? I need to, I'm just going to do that little commutative trick again. We can say this is now 1 greater than a multiple of 3. And so this is 1 mod 3 now. So this is 1 mod 3. And so what does that mean in terms of the diagram? It means if you're in the 0 state, 0 mod 3, and you put a 1, which corresponds to doing 2x plus 1, you end up in the 1 mod 3 state. So I'm going to put an arrow like that. All of that to say that's where the arrow goes. All right. Sorry, I'm going to have to keep on scrolling up and down. Okay, and I'm going to try to do similar reasoning to this. So that handled the first state there. How about now if x equals 1 mod 3? Then, before I wrote x equals 3k, how would I represent this situation now? Similar to that, but x equals 1 mod 3. Yeah, so then x is 3k plus 1, right? If x is 1 mod 3, it means it's one more than a multiple of 3. So then I can write x equals 3k plus 1, all right? And so if we see a 0, we get 2x, which is, 2 times 3k plus 1. We've got to do a little distributing here, all right? I'm trying to figure out what extra, left over after a multiple of 3. So distribute the 2, I get 6k plus 2. And what is that when we go mod 3? Show me the fingers. 0, 1, 2. I see 2s. I think 2. Yeah, this, if you go mod 3 on that, the 6k part will disappear and you get 2, right? If you like, you could say this is the same as 3 times 2k plus 2. It's 2 more than a multiple of 3. Are you into this mods business? I hope so. This is 2 when I go mod 3. All right? So that means on the diagram, from this state, x equal 1 mod 3, the 0 arrow goes to the 2 state. All right? Fill it in like that. And then I'm also going to consider from that state, what if I see a 1? Where does that arrow go? Well, all right, we do the same thing. So if we see a 1,
Did you get to do with 1 not a 0?
did I?
Doesn't 0 go back to itself?
No.
No.
Now, in this case, I think what I wrote is correct.
Isn't 0 double it?
Yes, and if it was 1 mod 3 before and you double it, it becomes 2 mod 3. Really, the reason is because of all of this. But if it was 1 more than a multiple of 3 and then you double it, that you had an extra 1, it becomes 2 extra because you doubled it. Yeah. Yeah, you have to sort of work the algebra a little bit. Let's see what happens in this case. From the same state, if I had 1 mod 3 and I see a 1 next, then we get 2x plus 1. But x is 3k plus 1, so this is 2 times 3k plus 1, right? Distribute that. I'm trying to unravel what's the extra leftover part beyond multiples of 3. This becomes 6k plus 2 plus 1, which is 6k plus 3. And that actually is a multiple of 3, right? And so this is 0 when I go mod 3 on that. If you like, you could factor the 3 out. It becomes 3 times 2k plus 1. And so this really is a multiple of 3 equals 0 mod 3. And so that means the arrow here, this is an arrow labeled with a 1. It should go back to the 0 state from the 1 state. All right. None of these arrows are really obvious where they should go. You have to work the details out. Okay, and then finally, the last state there, x equals 2 mod 3. We go through two different cases, just like we have for all these other ones. So finally, if x equals 2 mod 3, then to write x, it would be 2 more than a multiple of 3. So I say x is 3k plus 2. Yes?
Sorry, so
Did I-
on the diagram, is there supposed to be a 1?
Did I draw it wrong? Oh yeah, I put 0 both times. That should have been a 1, this one. Yeah, thank you. I saw some confused faces, becoming increasingly more confused. Thank you for that. All right? Okay. Anyway, for the final state, x equals 2 mod 3. That means x is of the form 3k plus 2. We do the same business. What happens when you go to 2x? So if we see 0, we get 2x, which is 2 times 3k plus 2 And if I rearrange everything so that it looks like a multiple of 3, distribute the 2, you get 6k plus 4. How can I write that in terms of multiples of 3? I guess this is, I would do 6k plus 3 plus 1, which is 3 times 2k plus 1 plus 1. Anyway, this is 1 when you go mod 3, right? It's probably easier to just look right here. If I start with 6k plus 4 and I reduce this mod 3, the 4 becomes a 1 and the 6k goes away because it's a multiple of 6. Anyway, this is going to be equal to 1 mod 3. It is a multiple of 3 plus an extra 1. So that arrow from the 2 state with a 0 goes back to the 1 state. And finally, one last thing. From the 2 state, if I read a 1, if we see a 1, we do 2x plus 1, which is 2 times 3k plus 2 plus 1. This is 6k plus 4 plus 1. That's 6k plus 5. And when I reduce this mod 3, I get 2. The 6k is a multiple of 3 already, and the 5, when I reduce mod 3, is equivalent to 2. This is 2 mod 3. All right. So that means from the 2 state, if you read a 1, it stays in the 2 state. Like that. And that's my final answer. This is the whole DFA. It tells you if a number is divisible by 3 or not. All right. Maybe could we just try an example? For example, 12 in binary. Maybe I'll just do a little sidebar here. Example 12 is, I have a hard time. I don't have these binary numbers memorized, but I wrote it down last time, I think. 1100, is that right? I think that's 12. Is that accepted or rejected on the diagram? You can just kind of dance around with your fingers. So you're going to start over here in the 0 state. I read first a 1, so I go over to the right. I read another 1, I go over to the left. Then I see 2 zeros, I loop back here twice, and I end in the accepting state. So it is accepted, which it should be, because it is divisible by 3. Whereas something like 16, I happen to know 16 in binary is this, because it's 2 to the power 4. Is that accepted or not? It is not accepted, because you would start here, you do 1 first, and then a bunch of zeros, which goes back and forth here to here, but it's not going to be accepted. It's not going back to the original accepting state. So this is also, or this is rejected, which is also correct. That's what we want it to be. All right. I feel good about that. Any thoughts about this one? So, yes?
Could you do this kind of divisibility thing with any of them and just like have a number of states as the number you're talking about?
Yeah. Actually, our next homework assignment is going to ask you to do it for divisible by 4 and 5. Really, it's not hard to do. You just, for divisible by 4, you need 4 states. And you go through this same reasoning. Yeah, or 5. Mm-hmm. Yes?
We need to take into account epsilon too.
Yeah, so this is a good question. He said, what about epsilon? Epsilon, the empty string, in this case, the empty string on this DFA, the empty string is accepted. So this makes sense if you interpret the empty string as representing the number 0. So if you allow that, of course, I also interpret the number 0 as representing the number 0. So, but the empty string, if it is interpreted as 0, then this works exactly the way you want it to. If you don't want the empty string to be counted, to be accepted, then you would need an extra sort of rejecting state just to begin with to capture the empty string, which leads into these states immediately afterwards. But I don't want to deal with that. All right. So this, I intended for this to be an example of a DFA, which actually does something that's kind of a hard computation. It's not super hard, but it's interesting at least. Do you have another question?
We'll have to check for grammatically correct binary numbers. For example, if we have 3 0, it doesn't make it's not a binary number.
Right. Yeah. So this is also something like you might worry about. What about things like 0 0 0 0 1 0 1? Is that even a legal number? I would say this is socially awkward, but still a legal way of writing a number. So I'm also going to interpret numbers with zeros on the left they still are allowed. And actually, they will still be accepted in this DFA. Any extra zeros on the left will just result in loops at the beginning, and then you do all the other stuff as you would have. So yeah, that's a good thing to think about, but I don't want to worry about it. All right, excellent. Yeah, if you wanted to prohibit strings like that, you could just make a new starting state, and then if the string begins with a 0, you make it go to a permanent failure. Unless it begins with only a 0, in which case it should be accepted. You could do that. I don't want to get into it though. It's not really difficult. You just need a few extra little states to check it at the beginning. All right, excellent. Let's talk about something a little bit more abstract. We have discussed DFAs. Nobody really objected when I said this, but I'm going to just ask the question, what really is a DFA? The way that we've been describing them so far is a DFA is like one of those pictures. It's got some states and some arrows. All right. One thing that you may have gathered in your mathematical career so far is mathematically, we don't like to define something using a picture. We don't like to define things as pictures. Pictures are generally regarded by mathematicians as being imprecise. The picture carries all of the necessary information about the DFA, but the true nature of the DFA is not really the same as a picture. For example, this DFA, how about this one? This is a DFA which accepts all strings of A's which have even length, right? Consider that DFA versus this other DFA. Check it out. Now, all right, those are two DFAs. If you ask me, I say those are the same DFA, but they're actually not the same picture, right? Like the one on the right is longer. You should say that's stupid though. Like that's not really an important feature of the DFA. That's just how you drew it, okay? And this is true. This is stupid. This is also, you could do something like, how about this? How about that, huh? How you like that? Or, I don't know, maybe I could draw this one with like straight lines, right? That is also the same, I made them go in the same direction. That's really not allowed. That's also the same DFA though, all right? What I'm trying to convince you of is the DFA actually is not just a picture. We think of it as a picture, but the picture is not what it is. Then what is it, if not the picture? It is, there are many ways that you could describe this, but the way that mathematicians like to describe this in terms of its true nature, the true nature of a DFA is not the picture. The picture is a representation of the DFA, but you can draw the same DFA in different ways, and it's still the same DFA. The true nature of a DFA is given by certain sets. If you've ever talked about, you probably talked about graph theory in some of your other classes, and this is another thing about graphs in general. A DFA is really kind of a graph with some extra information on it. A graph can be drawn, you can draw the picture of a graph, but at some root level, the definition of the graph is by certain sets. It's got a set of nodes and a set of edges, something like that. And that's how the true nature of a DFA is defined in terms of sets. And this is actually important sort of historically. Remember what I said about the history of the subject. People had been thinking about algorithmics and algorithms for a long time. The big advance that was made by Turing was to find a way to express what an algorithm is purely in terms of sets, not just in terms of drawing pictures or saying, hey, you know what I mean about like do a bunch of steps one after another. That's all wishy-washy. You got to define things in terms of sets. Usually in mathematics, all of modern mathematics is built upon set theory. And so when I talk about giving a real definition of something, I usually mean in terms of sets. Certainly in this class, everything is based on set theory. So the true nature of a DFA is given by certain sets. And so what we're going to talk about for the rest of today falls under the heading of the formal definition of a DFA. All right. Usually you think of the DFA as the picture, but the picture is not actually what it is. It has sort of lurking underneath, it has a true definition in terms of sets. And I would like to think about, so maybe I'll just for fun, I'm just going to draw this one again. I need to somehow take that diagram and express all of the important ingredients in terms of sets. So I'm going to try and write down, what are the important ingredients? Actually, there are 5, according to the way that we're going to write the true definition of the DFA. There are 5 important ingredients which are expressible in terms of sets, or maybe elements in those sets, or something or other. Anybody want to say what are? I don't mean that particular DFA has 5 of them. I mean all DFAs can be boiled down into 5 different things. What do you think?
I was thinking like an accepting state.
Okay, so yeah, one of them is which one is an accepting state. Although actually there could be several accepting states. So I'm going to say there is a set of accepting states. That's one of the ingredients. What else?
Like where's the start?
Okay, the starting state, and that's not a set. That's just one state, right? There has to be one particular starting state. All right. What else? What do you think? The language, yeah. What are the A's and B's? You mean? Yeah. So I would say that's we're going to call that the alphabet. Like in that particular example, the alphabet is just A, right? That's the only letter. So the alphabet. What else? Yeah?
The transition arrows?
Yeah, where the arrows go, all right? This is the transitions. And there's one more. Yeah? Yeah, the rejecting states. So somebody already said the set of accepting states. You also need to know what are the rejecting states. Actually, in the way that we formulate this, as in terms of these 5 ingredients, we are just going to have, you mind if I squeeze this in on the top? The set of all the states. So you can figure out which ones are the rejecting. We're going to specifically list out all the states and then say which ones in particular are accepting. If you want to know the rejecting ones, you can figure it out by excluding the accepting ones. All right? These are the 5 ingredients. So here's my definition. Actually, in the definition, they're not going to go in that same order. I was just writing them in the order that you all said them. But here's the definition. A DFA is defined to be a 5-tuple. That means like a pair is 2 things, a triple is 3 things. This is 5 things. A quintuple, you could say, but I don't want to have to remember all those little words. A 5-tuple. I'll call the whole thing M, and it equals these 5 things, and we are usually going to write them this way: Q, sigma, delta, Q naught, and big F. Where I'm going to tell you what each of those things represent. Q is the set of states. So I'm going to say this is a finite set, which we interpret as meaning the set of states. And it has to be finite, as we know. That's the F. It puts the F in DFA. The set of states must be a finite set. Sigma is the alphabet, which also is just another finite set. and this is the alphabet. Delta represents the transitions. Now, you could think of the transitions as a set of arrows, but actually it's more convenient to think of the transitions as a function, which tells you how do you get from here to here. You think of that like a function rather than as a set of arrows. And so I'm going to say this is going to be complicated looking, but I'll write it first and then we'll talk about it. How do you like that? It says delta is a function, and I'm writing its domain and codomain. I hope you remember your discrete math class when you wrote things like this a lot. The domain is the Cartesian product, Q cross sigma, and the codomain is Q. So what this means is delta takes a pair as its input, where the pair looks like a state followed by a letter. And then the answer is another state. That's what I'm saying. I'm saying the domain is the set of pairs. Remember, the product in set theory means the set of pairs. The domain is a set of pairs where the first thing is a state and the second thing is a letter in the alphabet. And this says delta is a function which takes a state together with a letter in the alphabet, and it gives you a state as the answer. And the interpretation of this is, this tells you, if you're in some state and you see some letter, this tells you where the state you go to is. That's what the answer represents. And this is called the transition function. It is combining all the information and all the arrows together into one big function, which just tells you where each of the arrows go. From this state, when you see this letter, you go to this other state. That's called the transition function. All right, those are the three ingredients. The delta is the most complicated one. What about the others? The Q0 is the starting state. Q0, and really what it is it's just an element of Q. It is a particular element of Q. And this is interpreted as the starting state. And then finally, F was the last thing. Sorry, I scrolled it. F was the last thing, and F represents the set of accepting states. And as far as what F is, it is a subset of Q. Q is the set of all the states. F is allowed to be any subset of Q, and this is the set of accepting states. All right. Once you put those things together, that's what the DFA is. This encapsulates all the information on the DFA. All right, I'm going to do a couple examples. So one thing you can do is I could show you a picture, and then your job is to translate it into this formalized description. Or we could go the other way around. I show a formal description, and then you translate that into a picture. By the way, nobody asked me, but I will remind you. I don't know why this just came to me. I expected someone to say, is this going to be on the quiz on Friday? The answer is no. The quiz covers just what was on the homework. So nothing from last time or this time. Okay, I interrupted myself with the question about the quiz. All right. This is the true nature of a DFA. This is the formal description of a DFA. So let's try an example where I draw the picture and you have to come up with the formal description. So let's say this is the picture. I'm going to have three states here. Two of them are accepting. Sorry, I meant for that to be a B here. Doesn't really matter, but I might as well write what I wrote on my paper. Like this, all right? This is a DFA. I don't know if it's easy to describe in words what that DFA accepts. Something which has a B. Oh no, this rejects anything with an A after a B. So this accepts things which have a bunch of A's followed by a bunch of B's, and that's it. Whatever, I don't care about that at the moment. I would like to try to translate this into the formal description. So I'm going to say, write this DFA formally as a 5-tuple, all right? Yes?
Can we name the states or something?
Yes, you have to name the states. You know, the first thing you're going to have to write in this list of 5 things is the big Q, which is the set of states. You're going to have to give names to these states. And you can call them whatever you want, although I'm usually going to use S1, S2, S3. But you can call them anything you like. Sometimes I go STUV, whatever. For now, I'm going to call them S1, S2, S3. All right? Because my name starts with S. No, it's because S is for state. Okay, what are the ingredients? So the hardest part of this, and let's just get to the hardest part first, because all the rest is pretty simple. The hardest part is the delta. Actually, let's leave the hard part for the end. Let's talk about Q is the set of states. There's the sigma, there's the Q0, and the F. All right, I'm going to postpone discussion about the delta. What is Q in this case? It is the set of all states. Make sure you get your brackets and everything right. It's that. The set S1, S2, S3. How about sigma? Anyone want to tell me what is sigma? What is it? Yeah, it is the set of A and B. Anybody want to put a star on that? I don't know if you want to. You shouldn't. This is the alphabet, which is just what are the letters, the individual letters. If you put a star on that, it means all possible strings. But that's not the alphabet anymore. That's too much stuff. I just want A's and B's here. Okay, Q0, that's the starting state, which according to the diagram is apparently S1. That should not have the brackets around it because Q0 is a specific state, not a set of states, just a state. And then F is the set of accepting states. This one should have the curly brackets around it because you're going to have to write down S1 and S2. All right. And what about the delta? Well, let me just say, so the DFA is, when I write it as a 5 tuple, it looks like this. First I put Q, and you have to write them in the proper order. The first thing is a set of states, followed by the alphabet. It's this. Followed by the delta. Now I haven't said what delta is yet. I'm just going to put a delta there. And then down here I'm going to say where delta is, etc. We'll do that later. But anyway, after the delta comes Q0, which is S1, followed by F, which is S1, S2. When you write out the DFA formally, it looks like just a bunch of nonsense, a bunch of like little sets and elements and stuff like that. It doesn't look anything like the picture, but that's the point of this. The whole reason we want to do it this way is so that we don't make the definition in terms of the picture, all right? Although, practically speaking, you usually want to think of it as the picture because it's just much easier to visualize. Anyway, next you say where the delta is, and here I have to describe delta is a function, right? Remember the domain is pairs with a state followed by a letter. And so the only way to write that function, usually like in a calculus class, you write a function using some kind of equation, sines and cosines or whatever. There's definitely not going to be sines and cosines here. How do we say what the function is? Well, there's no formula for it. The only way is just to write down every possible value of the function. So delta is the function which is given like this. Delta of S1 and A equals delta of S1 and B equals. And you just have to say what all the values are. This can be a pain sometimes, although it's not so bad in this example. S2A, S2B. I'm writing all possible pairs where the first thing is a state and the second thing is a letter in the alphabet. There are 6 of them in this example because there are 3 states and 2 letters. And then you just got to say each time what the answer is. And when you see this, delta of S1A, what that means in terms of the diagram is if you start in state S1 and you do A, what state do you end up in? And if I look at the diagram, it was S1 again, right? S1 goes back to itself with the A. So delta of S1A is S1. Delta of S1b is S2. According to the diagram, if you're in S1 and you see B, you go to S2. And so on. So this is not hard, it's kind of a lot to write. Delta of S2a, that one was S3. Delta of S2b is S2, and S3 stays by itself, so it's like those. S3 and S3 for the last two. All right? This is the formal description of the DFA. I fit it all on the screen. All right? This is the true nature of the DFA. Do you like this better than the picture? No, you shouldn't really. Sometimes when you see somebody's true nature, you like them less. that's kind of the case here. But so I'm going to say this is, from a formal mathematical point of view, this is a preferable description, even though when you're trying to actually think about the DFA, the picture is better. But from a formalistic point of view, this is, theoretically speaking, a better, more firm foundation to consider the DFA on. Yeah?
So when you put it into the table, are you putting the solutions in? Or do you put the entire thing?
Well, this is as good as it gets as far as writing this. You can't really shove all of these into that position, if that's what you're wondering.
Okay.
Because what goes in this position is a function.
Okay.
Like the name of a function. So this is really as good as it gets.
Okay.
Yeah. You know, ordinarily, if this were a more sort of, if this were like a calculus class, you might imagine putting a function in here, like instead of writing delta there, you could write something like f of x equals x squared, right? That's a function which has a convenient formula which you can fit right in there in one line. But in this class, it will never have that kind of a convenient formula. And so your only option is to just write out all the values down below. Yeah.
Do we have to write the domain and codomain when we write about?
I would say you don't have to. I mean, the structure of a DFA, it is, the domain and codomain must be what I said before. It has to be Q cross sigma going to Q. So you don't have to write it every time. Although if you want to keep it straight, that it's not a bad thing. All right. We got 8 minutes remaining. I want to talk about some cute properties of this delta function. So this is the formal description of a DFA. I also, we're not going to get to this today, but I also, for next time, we'll define L of M formally using the sets stuff. This is the language accepted by the machine. You know, if I ask you, just informally speaking, what does it mean that a string is accepted on a DFA? What you should think is, on the picture, if I move my finger around, it ends up back at the accepting state, all right? But how exactly do you say that in terms of the formal sets stuff? That's what I want to talk about eventually. Towards that end, something we can talk about in our remaining 7 minutes, I will just say it involves doing delta over and over again, right? Because it involves reading a whole string into the DFA, not just one letter, but several letters, one after another, and kind of jumping from one spot to another in the DFA. And so actually there's another notation that we use. So delta represents a function which tells you what to do with a single letter, and it's called the transition function. We're also going to discuss something very closely related. We have what's called the extended transition function. The extended transition function, and the way this one works is you can do delta of, say, S1, comma, ABA. And this one, the extended transition function we write with a star, delta star. This means something different from the star that we used before for the alphabets and languages. But actually, generally in this class, star always represents some notion of repeating something, doing something over and over again. And what this represents is, what if you start in state S1 and you do that whole string, where do you end up? And in our example, if I follow the diagram, ABA, I end up in S3, right? If I start in S1 and do ABA, it ends up in S3. This is called the extended transition function. So this one, its domain and range are a little bit different. The domain is still a product. It's Q cross, but this time, the second element is a string, not just a letter. So it has a star in the second coordinate, all right? The ordinary delta does not have the star there. That's because the second thing in the pair is just a single letter. But the delta star, the second thing in the pair, can be a whole string. And so its second coordinate comes from sigma star, which is the set of all strings on the letters from sigma. All right? So what this does is the answer, I will just describe in words what this means, is where we end up after reading the whole string. All right? And I have some simple properties of delta star. The first one is very easy. The second one is still pretty easy. And the third one is a little weird. Hopefully we have enough time to do these in 4 minutes. All right, first one, very easy. Anybody want to tell me what should the answer be? Delta star of Q comma epsilon. Q is a state, and I read epsilon, that is the empty string. Where does it end up? Q, yeah. If you start in some state Q and you read no letters, where should it end up? Still in Q. All right. That was the very easy one. Next one. How about if my string actually is length 1, then delta star of Q comma X. So if X is a string which happens to consist only of a single letter, then delta star is actually just the same as the ordinary delta. Right? That's because if the X is a string, but if it really is just one letter, then what we're talking about here is not any different from the original delta function. Okay? And then, the tricky one. We got 3 minutes. I think that's enough time. I want to try to express what happens, delta star is what I mean here. If you start in state Q, and then you do X followed by Y. Can I rewrite that somehow? Here's what I mean by that. I want to write something like, isn't that somehow like doing Q and X followed by Y? Like if you start in state Q and you do X followed by Y, I want to express that somehow as like, okay, first you do X, and then from there you continue and you do Y, all right? This, what I just wrote, is bogus though. That's not what it should be. Can anyone tell me what's bogus about that? Yeah, what do you think?
Oh, I was going to give you an answer. I'm going to give you a potential answer. I don't know.
Oh, okay. Can you say what's wrong with that?
Wouldn't you be starting in like the same state like both times? Like don't you have to go from X and then to Y?
You go from X and then to Y. Yeah, this
Because
is...
doesn't that mean you're going to X, but then from the same string state you're going to Y?
Yeah. Like this Q shouldn't be here both times. Is that what you're saying? Like maybe this one should be something else. But actually, there's even a deeper problem here. Like this is what I wrote. Just doesn't make any sense. What does that mean when I put these next to each other? This is like plus here, multiplication. You can't add those. Whatever you think that means is not what it means. You can't combine them in that way. So how you write this, I hope everybody is clear on the idea of what I'm trying to say. What I'm trying to say is you start in Q, you go through X, and then from there you continue and go through Y. How can we actually write that? You got an idea? Uh-huh. I like this. I knew we could do this in 3 minutes. This is complicated. What does it mean? You have to kind of read from the inside out here, all right? From the inside, this means where we end up after x, right? Delta star of qx means that's where you end up after you read x. And then that is where you start and you follow it by y. All right? This is how you have to write that. This is I would say, the idea of it is not that strange, but when you write it, it has to look in this weird way. Yeah?
Could we not do the star like you did in number 2?
Leave the star out here.
Yeah.
In this case, I am thinking of x and y are both two different strings, perhaps long strings.
Oh, we don't know if they're not.
Yeah, it's not a single letter. It's just any big string. Yeah, so you need this star both times. All right, excellent. We'll talk some more about this next time. See you then. Let me know if you got homework questions. It's due tonight.